All right, good afternoon, everybody. So I hope you guys are awake, caffeinated and all. So let's go on this world tour of high contrast imaging instrument concepts. There is a lot of action going on right now, as most of you know. I would like to thank these people here for sharing proprietary material with me to show you. So this is a great privilege to be able to present all these exciting new instruments coming online these days. So I'm going to spend a very short amount of time on trying to convince you that high contrast imaging is the richest technique for exoplanet science. So you're here today and this week because most of you are convinced of that already. That's my hope. I'll spend some time explaining why I believe HST is the mother of all high contrast imagers. And I'll spend even more time then on the basics of high contrast imagers, the building blocks, so the whole system level aspects of high contrast imaging. Not only coronagraphs have wavefront control, but the whole system starting from the telescope to the final science-reduced data. Highlights of first generation high contrast imagers, scientific results that you all know about, so I'm not going to spend too much time on this. Second generation high contrast extreme AO imagers are here today, so all of them have come online over the past few years and very recently in the case of Sphere. And I'll spend a little bit of time on the future. So let's get started right away. So why is high contrast imaging so important, so amazing? So you get to do all these measurements at once. So once you've managed to isolate the signal of an exoplanet from its host star, you get to do astrometry, spectrophotometry, and polarimetry in some cases. And most importantly, you are able to put the planet into the global context of its circumstellar environment, and in this case, disk, which is quite amazing. Now, if you add the temporal aspect to these measurements, or if you repeat them over time and time again, so you get to resolve the orbit and study the dynamical stability of systems. You might be able to resolve weather phenomenon, dynamical phenomenon in the exoplanet atmosphere. We are starting to do that with the brown dwarfs. And you might even be able to resolve in time the variability of circumstellar environment due to interaction with planets. That's something that's been done already with the protoplanetary disks. And so we'll get, I'm absolutely convinced of that, we'll get to do this more and more in the future. For all these awesome reasons, high contrast imaging is the most difficult technique and probably the reason why it's coming so late to complete the big picture. So there's been many imagers out there that have started to do high contrast imaging without being designed specifically to do that. First, you have HST with a series of cameras. Some of them were equipped with LEO coronagraphs, so now you know everything about LEO coronagraphs. And you see here a bunch of ground-based instruments, some of them equipped with first-generation adaptive optic systems, and some of them equipped also with coronagraphs, starting with LEO. So you see that's the widespread, most used coronagraph ever. But you see some exotic names here that Jeremy introduced in the previous talk. So I'm going to describe a little bit some of these workhorse instrument and major observatories. But I will start first with HST, which is in this privileged situation outside of the atmosphere. And it's not only its position that is producing these amazing results that we've all seen for the past 25 years. That's also the fact that HST is equipped with 3 fine guidance sensors, and that's something extremely important to high contrast imaging, and that will come back over and over again. These fine guidance sensors, multi-million-dollar equipment, are ensuring 1 milliarc second pointing accuracy over timescales of regular typical exposures for HST, which is 1/100th of the size of the point spread function of the telescope. So for this reason, the PSF stability and pointing on the coronagraphs of HST is extremely good, and so good that we can go back in the archive and re-reduce the data and use all the information we've accumulated for all those years to subtract the coherent background of speckles down to unprecedented levels, reaching down to the photon noise limit. So I invite you to go see LOD is poster and pop presentation, and around talk we're going to talk about this initiative, the ALICE project, which is to go back into the archive and try to combine the PSFs in the most efficient way to reveal new candidate companions and pictures of very well-known disks with unprecedented inner working angle and sensitivity. So we've learned so much over the past few years about HST and PSF subtraction and observing strategies thanks to synergies between ground-based and space-based, that now new programs are revisiting these very well-known objects, applying these new techniques, pseudo-angular differential imaging, for instance, and PSF combinations to reveal known objects with unprecedented sensitivity and inner working angle. This is quite amazing. So now the playing field is not level at all. From the ground, we have to image these objects through a mess of turbulence. 100 kilometers of thickness of our atmosphere is actually blurring all of our images, and it's very hard to do high contrast imaging through the atmosphere. So we need a lot of subsystems. So your instrument is composed of many, many things. Here I've listed a few. I'm not being exhaustive. I try to be. So you have the telescope, coronagraphs, deformable mirrors. It's all put there for you to see. There is no particular order here, but order does matter. So, of course, you start with the telescope in space. So far, we haven't done any wavefront control per se, so we go directly to the chronograph and then the science instrument. On the ground, we have to go through all these systems that are just there to correct for the effect of the atmosphere on our images. So we have derotators to compensate for the rotation of the sky on ALTAS telescopes. We have ADCs to correct for the dispersion of the atmosphere. We have a set of relays that send the light into the adaptive optics system, which is composed of tip-tail mirrors to correct for pointing errors, deformable mirrors to correct for higher order aberrations introduced by the atmosphere. All these correcting elements are driven by sensors that get some of the light from the sense, usually in the visible regime, where we can have fast cameras, but we can do that now in the infrared as well. And the rest of the light, so either part of the visible light that wasn't used by the wavefront sensor or the infrared, goes through the chronograph down to the science camera, spectrographs, polarimeter, whatever. So we have this closed loop here. The wavefront sensor is after the correcting element, so it's measuring 1,000 times per second the result of the correction by these elements, and there is a feedback between the wavefront sensor and the deformable mirrors. So that's how first generation adaptive optics system work, and that's also how a second generation adaptive system works. So there's been many instruments based on this concept. It's very successful. You see here, you recognize some of these building blocks here. This is NAOS Konica, the VAT. It's been online for more than 10 years now. It has produced many results. It contributed to 3 of the top 10 discoveries of ESO. So the discovery of the first exoplanet, the imaging of the galactic center and resolving the orbits of the stars around the central black hole, and many, many other things. In the northern hemisphere, Subaru has a system which is analogous to NACO, or always the same story. So once you understand this architecture, you can look at any of these drawings and understand them very quickly. So I've put them up here for your records. I'm not going to go through all of them, because the architecture is always the same one. The devil is, of course, in the details, and in the case of Subaru, the wavefront sensing is done a bit differently with the curvature wavefront sensor. So I'm not going to go into the details of that, of course, but this is quite interesting to see how these systems differ. So we have KEK AO with NERC2. The characteristic here is that it's on a table, the Nasmith focus, so it's pretty stable. So you have to derotate the pupil and image with the derotator here, which is a big difference with NAOS Konica, for instance, which was directly attached to the telescope derotator. So the whole instrument was actually rotating when tracking, which induced flexures, for instance, which we don't see in NERC2. So there has been a few systems recently that what I call transitional systems, like Nikki. We introduced SDI, spectral differential imaging, simultaneous differential imaging. So the letters, the acronym works for both simultaneous and spectral. to the mainstream. So this is a very nice instrument, produced interesting results recently. So this was really this transition instrument between the first generation and the second generation that we are seeing now. There's been some interesting experiments at Palomar using the adaptive optics system of Palomar. So a few years ago, Jean Servid had this neat idea of reimaging a 1.5 meter portion of the primary mirror and relay that to the adaptive optics system without telling the adaptive optics system that it was only correcting 1.5 meter instead of 5. So the result was a stray ratio, so this metric that we use to characterize image quality and how close it is to being perfect. So 90% stray ratio on typical bright stars, magnitude 5 in V. And so you see here, this is a sky image of the point spread function delivered by the system. So we had a lot of fun with it and did some coronographic research using this wonderful image quality. So first generation instruments also have still a lot of untapped potential, in my opinion. There are a few posters about that. L-band, 4 microns. There you get, with these old systems, you get very high, excellent image quality, very good image quality, and you can use coronography on these beautiful PSS at 4 microns. So you get this for free, and so if you look into the numbers, you see that there is, because of the thermal emission of young planets being higher at 4 microns, it's intrinsically, you can actually get almost the same sensitivity in most of the cases as second generation instruments. So there is a nice overlap complementarity here of first generation instruments with second generation instruments. So we've started to work on that, and there has been a few new generation coronagraphs installed at the VLT, LBT, and in the future at Keck to exploit this good image quality at 4 microns. A few posters on that as well. So these are results that we've obtained with this system. And so this is the disk of beta pictoris at 4 microns, a beta pictoris B with a vortex coronograph at 4 microns. So this is something that we are going to exploit in the future because it provides this nice complementarity to the new generation systems. A few scientific highlights from these first generation instruments. So you've seen these images before. Here are a few more. Discs at Subaru, quite spectacular in polarization, differential polarization imaging. Niki, the multicolor image of Niki for HR 4796. So very impressive results. So now let's go into the actual excitement of these new instruments coming online. These are called Extreme AO, like Jeremy said, because we have put all the subsystems on steroids. Basically, we have a high-density deformable mirror. We have high-density, low-noise, faster wavefront sensors. We have better optics. These instruments are optimized for stability, the lesson from Hubble. We have speckle control strategies which are fully built into these instruments now. So this is a summary of all the instruments that I'm going to consider in the following. So P3K at Palomar, Sphere at the VLT, GPI, Gemini South, Skexeo at Subaru, MAGEO at Magellan, and LRMICAM at LBT. So there are a few talks and contributions during this week about this subsystem. I'm just going to highlight a few things about them. So the deal really with these second generation instruments, apart from the fact that they are on steroids, is that we want to deal with these speckles. There are two ways to do that. So Jeremy mentioned briefly image plane wavefront sensing. So the idea there is to sense the electric field at the sense camera level and compensate for it with the deformable mirror. So you get rid of it before you record your sense exposures. The other way is to actually do differential imaging. In practice, all of these new generation instruments do a combination of these two strategies. So the architecture is very similar to first generation instruments. So a few elements have been upgraded here. But you see that there is this feedback loop now from the sense camera to the controlling element. And this is really the critical part here. So we want to measure exactly what's going on at the camera level and to distinguish speckles from planets. There is also some feedback in some of these systems from the coronagraph to the correcting element. So we want to make sure that not only The image looks extremely good at the camera level. There are no speckles there, but we want to make sure also that the star is pointed at the chronograph as perfectly as possible. By the way, this architecture now is actually the one that's going to be used on next generation space-based chronographs as well at a much smaller pace than 1 kilohertz that we need to use to compensate for the turbulence in the atmosphere, but it's still going to be very similar to this. One thing that's very important in those instruments and architecture, it's the instrument control software, something that's not presented because it's a bit boring, but it's absolutely critical that we have excellent control software that's going to make all these elements work together perfectly. The user interface is also very interesting. If you build your instrument and you arrive at the telescope and nobody can use it, then you're screwed for the next 10 years. So you also want the data flow system to be consistent with all the rest. So all the information from all those subsystems transmitted to the archival system, the pipeline has to work, etc., etc. So let's not forget about these very critical aspects here of next generation instruments. The environment is something that's also critical and not always getting a lot of attention. Your instrument might work perfectly in the lab, and when you arrive at the telescope, you are confronted to many environmental conditions, problems, telescopes, interactions that were not foreseen because you are exploring new regimes that nobody had done before. So it's something that you are learning on the spot. So here you have locations for those telescopes, for your records. The focus is very important because it will determine the stability and the requirements on the stability for your system. The telescope system itself is very important. Like the P3K at Palomar has this limitation that the other subsystems don't have. It's an equatorial mount, so it means that ADI, for instance, is precluded at Palomar. So you have to be smarter and do something else. Okay. So GPI is small and lightweight. It has to be because it's the Casgreen focus. Its direct competitor Sphere has chosen a completely different approach because it's on an ASMIS platform, so it can be heavy, very stable, and damped. So the difference here in weight between these two instruments is a factor of 10. So it's quite amazing that while doing the same science, they end up being completely different. So these are nice pictures from all of these instruments. So you have the combined focus at the LBTI, you have GPI at the Casgreen focus of Subaru, Palomar telescope with the Casgreen focus here. You have the Sphere instrument, which is huge, one of the biggest instruments ever to come to Paranal, occupying all the space on the NASMIS platform. We even had to actually increase the size of the platform to accommodate this instrument. This is Subaru here, Skexeo, and Mageo, also NASMIS focus here. So something that's not always expected, especially when you go at the end of the world and you expect the weather to be stable, the sky clears 260 days per year. This is a weather event that we had soon after the first commissioning of Sphere. You see temperature profiles as a function of days. This is the dew point and the temperature outside. So we got some frost outside, and people were totally crazy about this, and they thought that their instrument at the deformable mirror, which is very sensitive, would get affected by that. We have thermal control, and we monitor this temperature in real time, but that's something that you need to be aware of. In Arizona, they have to care about monsoon, which closes the facility for a few months. We have wildfires, strikes in Chile, and sometimes barbecues. So coronagraphs are allergic to dust. This is the summit for the future extremely large telescope, 20 kilometers away from Paranal. So we closed the domes, of course, when we did that. We have earthquakes. This is the list of earthquakes that happened in Chile after the installation of Sphere on the platform. So you see accelerations here up to 3.5 centimeters per second square, so it shook quite a lot. So your instrument has to be ready for this kind of events. And in northern Chile, we are waiting for a big one. So that's something also that scares us when it happens in Paranal. So this is probably the most important one. This is the interaction with the telescope. So during the first commissioning of Sphere, we noticed that the jitter residuals were 3 times as high as expected. So the consequence on the stress ratio was a loss of 10 to 15%, which would affect performance, especially at small inner working angle. And we found just a couple of weeks ago that we confirmed that the origin of this shaking jitter was actually due to the servo loop of the secondary mirror of the VLT. So the solution is simply to turn it off. So we don't do any field stabilization, M2 is off. And this forest of peaks, high frequencies here were actually created by electronic noise in the servo loop control of the secondary mirror of the VLT, which has been working like that for the past 15 years. And everybody was happy about it. It's simply the fact that we are exploring new regimes now, and we are seeing things that were invisible before to people. So we are learning along the way about the whole facility. So a few more drawings for Palm 3000 at P3K at Palomar. So the architecture is always the same one, so I'm going to go quickly through that. This one is a bit particular, Mageo at Magellan. It has an adaptive secondary mirror, which is great to do thermal infrared imaging, because you minimize the number of optics in your instrument and hot surfaces. LBTI also uses an adaptive optics secondary mirror. This is the combined focus here. Sends the light from the two telescopes down to the mid-infrared camera here, which is the one we used to do L-band imaging and high contrast imaging. And the rest of the light, so the N-band is going to NOMIC to do ring interferometry. So these amazing secondary deformable mirrors. SCEXEO, very complicated. I'm not going to go into the details. There is a series of posters about SCEXEO. So SCEXEO is using every bit of light that's coming out of the Subaru telescope, so from the visible to the near infrared, to do all sorts of interesting things. GPI, very neat instrument. I'm really impressed each time I see this picture. It's really neat to pack all these complicated subsystems in such a small space and being so stable. Sphere, on the other hand, is huge. The size difference is amazing. I think the two drawings are almost to scale. Sphere has this common path infrastructure where you have the adaptive optics system, and you have the beam splitter here that sends the infrared light down to these two subsystems, so the IFS and IRDIS, which is a classical imager with a field of view of 11 arcseconds. So don't forget that Sphere is not limited by its field of view like GPI is. We have a field of view of 11 arcseconds, and we observe simultaneously between this instrument, this camera, and the IFS. The IFS is covering Y2J, and the IRDIS is covering H. We can go up to H with the IFS, and then IRDIS is observing at K band. But we always have this simultaneous coverage in wavelengths and field of view. We have a visible path with Zimpel, which is a differential polarimeter working in the visible. This is a unique instrument. There is no other like that in the world. So we are doing adaptive optics in the visible with a coronagraph and differential polarimetry. So wavefront sensing for these instruments is divided into two main families. So we have classical Shack-Hartmann wavefront sensors with spatial filtering. I'm going to say a few words about that. And the other family is pyramid wavefront sensing with modulated or not. And in the case of Subaru, we have curvature wavefront sensing. So the difference between Shack-Hartmann and pyramid wavefront sensing is the way the light is sampled. So the Shack-Hartmann wavefront sensor samples the wavefront in the pupil and re-image each portion of the pupil to spots, for which we measure the centroid offsets. And from that, we can reconstruct the local slope of the wavefront. The pyramid wavefront sensor does this measurement, the splitting in the focal plane. And that explains why we have such a gain in sensitivity for pyramid wavefront sensors, especially for low orders, so tip tilt typically in low order modes. That's because the size here where you do the splitting is actually much, much smaller than in the Shack-Hartmann wavefront sensor. That's also a reason why all next generation adaptive optic systems are considering pyramid wavefront sensors, because they are so much more efficient than Shack-Hartmann's. Spatial filtering for Shack-Hartmann wavefront sensor is absolutely critical for high contrast imaging. So this is to prevent aliasing effect at the wavefront sensor level. So the aliasing is just that you measure low order aberrations that are just ghosts of higher order aberrations that are not correctable by your system. The solution to that is to put a spatial filter at the focal plane of your reference sensor. And as you close down this spatial filter, you see that the image gets much, much better. This is the contrast curve, sorry for the quality here, but you see that the deepest contrast here is obtained when the spatial filter is closed down. And this is done on sky during the first commissioning of Sphere. This is another image of this on sky dark hole. Probably the nicest one I've seen so far. This was an exceptional night during the first commissioning. This is YJH simultaneously here. Quite amazing images when you think that this on sky. The first time, the only time I ever saw images like that was in the lab at JPL. So when I saw that was on sky, I almost cried. So these wavefront sensor pack new cameras, new technologies. Sphere is really proud to have an electron multiplying CCD as a wavefront sensor camera that allows for very low readout noise and super sensitive wavefront sensing. So we closed the loop 2 weeks ago on R of 15.9, which is quite amazing. Of course, you cannot do high contrast imaging when it's so faint, but you still can correct and get diffraction limited images at that wavelength, at that brightness. So this is the theoretical curve for the Strel ratio as a function of guide star magnitude for the wavefront sensor, and we are right into the specs for Sphere. So it's going to be a very sensitive high contrast imager. DM technology. Here we have a lot of variety as well. So we have several families of deformable mirrors. These new generation chronographic systems, adaptive optic systems, use a cascade of 2 correcting elements for most of them, except for Sphere, who choose to do everything in one go with 1 deformable mirror. The adaptive optic secondary mirror have a lot of stroke and are very fast, so they don't really need this cascade either. So I'm not going to spend too much time on this. There is a great reference for DM technology, which is this paper from a colleague at ESO. So he describes all these DM technologies one by one and trade-offs and so forth and perspective for extremely large telescopes. So it's a very interesting paper. The problem for high contrast imaging is that we have these DMs on steroids, several thousands of actuators, and the problem is that when you have so many actuators, the probability to have a few failing is pretty high. And that's a huge issue for high contrast imaging. This is a pupil image at the LEO stop, so after the coronagraph. And you see all these bright spots here are dead actuators that are sticking out of the surface. And this is a huge issue, as you can see, because these are creating light leaks that are coherent, and they create in the image plane this set of fringes with speckles pinned on it. So this is really bad for high contrast imaging. Hopefully you can design a LEO stop mask that will cover most of them. So by the time this mask was designed between the acceptance test in Europe for Sphere and the time it arrived at the VLT, we had another one popping up here. So too bad, but it's still pretty good. Coronagraphs, Jeremy has talked a lot about that. I like to, this is something I took from John Troger. I like to put coronagraphs in this, what John calls gamut of coronography. So it's pretty nice because it divides the action of the coronagraph between amplitude and phase and where you actually do this action, either the focal plane or the pupil plane. So you have the amplitude LEO coronagraphs, which is a pure focal plane coronagraph. The hybrid is actually should be right here because it's also using a little bit of phase. You have the phase mask coronagraphs down here in the focal plane using phase only. You have the pupil plane with the apodizer, the shaped pupil, the apodized faceplate. And in the middle, you have those hybrid solutions. And you see that the next generation adaptive optic system use a lot of these, a lot of combinations of different kinds of new chronograph technology, which is great because we get to play with the nice toys. So these are the toys. So PIA here at SCXAO, you have the apodized LEO coronagraph. So this is the apodizer with the astrometric grid for GPI. And you have the masks at the focal plane. This is the LEO stop here. You have all kinds of very exciting technologies here for phase mask coronagraph. So calcite plates, and you have photonic crystals, subwavelength gratings, liquid crystal polymers. This is a picture of the APP, apodized faceplate, that's installed at the VLT on ACO. So see lots of room for technological development. That's actually really fun and exciting. So like Jeremy said, many coronagraphs are sensitive to low-order aberrations. That's why we have all these sensors. I'm going to briefly talk about that. Second order coronagraphs. I'm going to take the other one because it's okay. Second order coronagraphs, which provide very small inner working angle, are very sensitive to low order aberrations. So this is contrast as a function of the aberration level, and these are curves for different low order aberrations. So in blue, tilt, focus, astigmatism, coma, trefoil, and so forth. And you see that here, this is a 10-6 contrast level. You see that it's actually going up pretty quickly. This is, sorry for the scale here, it's a bit small, so it's 10-3 here, waves, RMS. So you get 10-6 raw contrast level for 1,000 of a wave RMS of tilt error. So this is telling you how sensitive these coronagraphs are to low order aberrations. Hopefully we can build the same coronagraphs to have what we call a fourth order sensitivity to low order aberrations. And this is the same. You took the first two curves here, tilt and focus, and they are culturally pushed down like that. So we gain a few orders of magnitude, made them insensitive to these, virtually insensitive to these aberrations. The PLC is quite a strange case because it's almost getting better when you get off center. So this is the sensitivity of the APLC to tilt, and you see that at different locations in the image plane, it's fairly flat, or it's even going down slightly here. So it's a very interesting coronagraph, and also a reason why it has been chosen as the baseline coronagraph for GPI and sphere, for instance, or P1640. Shape pupils and apodized faceplates, because they work in the pupil, are also very insensitive to tip tilt. If you have a fast camera, you can always recenter your frames afterwards. So the shape of the PSF is not dependent on the tip tilt error. So if you want to go after these small, very small inner working angles, you have to cope with this, and that's also a driver. That's a driver for low order wavefront sensing and pointing cameras. So this is how you can do it. So the idea here is to really point the star at the coronagraph and stay there as precisely as possible for as long as you can. So you can take some of the light just before it arrives on the coronagraph, and have a pointing camera right here. That's the solution that's been chosen by Sphere. You can use light reflected off the coronagraph if it's a bit reflective. You can use the light at the LEO stop. You can also combine the light at the LEO stop with the light from the coronagraph and do interferometry. That's the CAL system that's in operation at Gemini, not yet at Gemini, but at Palomar. So the Sphere solution here, very simple, a splitter before the coronagraph, an infrared camera, and you do centroid. It works extremely well. I've seen it on Sky, and it stays steady on the coronagraph for hours. You have the CAL system at P1640 at Palomar. This is the only calibrator interferometer in operation right now, and it's doing great. So I'm not going to go into the details of these schematics here. You can, just for your records. This is the operation of the CAL system at Palomar. So this is open loop. You see the coronagraph here. Closed loop. You center the star behind the coronagraph. Lots of speckles. You turn on your calibrator wavefront sensor, and you start to dig out into the speckles and do active wavefront sensing in this part of the image. And this is the end result. Another result from the CAL wavefront sensor, you see that one side of the image has been corrected pretty nicely, and it's keeping this setting for the time scale of observation, so it's doing great. This is the typical contrast you get after actively correcting for the speckles using this parallel wavefront sensor. Typically better than 10-6 raw contrast on Sky, which is quite excellent. GPI has a similar system. It's not being fully used right now, but hopefully it will be commissioned soon. Only this part of the wavefront sensor of the CAL system is used. It's using a low-order Shack-Hartmann wavefront sensor, taking the light from the coronagraph at this location. So there is a hole in the coronagraph. So this is a LEO coronagraph, so the science is reflected off to the science camera here. And some of the light, so the central core of the starlight, which is coherent, is sent to this low-order Shack-Hartmann wavefront sensor. The idea is to then take some of the light at the LEO stop and make these two beams interfere and measure the wavefront at the LEO stop location, and then feed back any drifts to the wavefront sensor and then to the DM for correction. SCEXEO has chosen this approach, taking the light reflected off the coronagraph, at least in the PIA configuration. these are lab results showing a stability of thousands of point spread function size. There is another solution, which is to take the light rejected at the LEO stop and do the same kind of measurements. This has also been demonstrated in the lab. There is a poster about this. It also worked in closed loop on sky with the vortex coronagraph, which is a great result. So now differential imaging, I think I'm going to skip this because there is a hands-on session about it. All I want you to remember about differential imaging is it's all about modulating, demodulating your astrophysical signal to disentangle between speckles from planets. So you can do that by taking advantage of the field rotation, the spectral behavior of speckles, polarization. You can use time and your library of reference images and so forth. A few preliminary results. I like this slide a lot. I hope the image quality is good enough for you to see the difference between what we used to do 10 years ago with first generation adaptive optic systems for disks and what we do nowadays with the same telescope actually and the AO system on steroids. Excellent results obtained by P1640 before everybody else. They were on Sky a few years ago already, and now they know their instrument very well, so they got the simultaneous spectra of all the planets for HR 8799. They developed new post-processing techniques, so S4, which is somewhat related to PCA, but not quite so. So this is the contrast in the radius wavelength space before and after speckle suppression. So you see here we are getting down to the 10-6, 10-7 regime, which is pretty impressive. LBT, the four planets of HR 8799, H-band and L-band. So again, L-band here is really strong, going strong. If you convert the contrast curves into mass limits using models, of course this is not perfect, but you see that L-band is actually getting more competitive than H-band, even though the contrast is actually much better in H-band. So L-band is definitely something that we need to have a look at in the future even more. And this is one of the things we want to do and we are doing at L-band is to put new generation coronagraphic systems, take advantage of the PSF quality and stability at those wavelengths, and image also these four planets. This system is now available at LBT. It has been commissioned. We're trying to improve it even further. There is a SPA paper by Denis Defrère about this, if you want more details. MAG-AO is doing visible AO, one of the first ones to do visible AO. There is a poster about that as well. This I like a lot. This is doing spectral differential imaging in H-alpha, so to look for creating objects. This is great stuff. I really like this. I think it's going to be great with Sphere as well and Zimpol, this visible camera at the VLT part of Sphere. Of course, GPI, you've seen that a lot. So beta pictoris B, excellent contrast curves, approaching 10-6, 5 sigma at 0.5 arcsecond, which is excellent. Another result from GPI, excellent paper by Marshall Perrin, published just a couple of weeks ago. Sphere had its first lights in May. We had a lot of fun at the telescope. It's still ongoing. Contrast results are preliminary here. It's 1 sigma, so it's doing a factor of 2 to 3 worse than GPI, but these are curves from the first commissioning, and I guarantee you that the curves for the second commissioning are much better than this because we've solved these vibration issues induced by the M2 control, and we got 92% Strel at H and a tip-tit RMS of 3 milliarcsecond, which is the spec. In terms of Strel, actually, we are doing better than the specifications. So this is a summary for you to take home. So I'm not going to spend time on this. I only have a few minutes left, and I'm just going to introduce the future of fine contrast imaging from the ground and in space. Just a few more slides. So this is a nice plot made and maintained by Peter Lawson, showing the planet-star contrast as a function of separation. And this is showing First generation adaptive optics systems up here, and HST, projections for JWST here. These are still simulations for P1640 is a real curve, real performance. VLT sphere and GPI are predicted performances from a few years ago. And you have predicted performances for the extremely large telescopes, and here for EXO-C, one of these chronographic cameras. How much more time? You're done. I'm done? Okay. So it's good. All right, so just 30 seconds more. So we'll hear about W1st AFTA on Friday. We'll hear about JWST on Friday as well. So lots of coronagraphs that will be flying very soon. The design for W1st AFTA that will be presented by Bruce on Friday. EXO-C that I just mentioned here. This is the backup to W1st AFTA in case the coronagraph is descoped. The starshed that you'll hear about in just a few minutes. And this is the slide I wanted to show you. This is the complementarity between ground-based extremely large telescopes, so the future of ground-based adaptive optics and high-contrast imaging, and space-based coronagraph. So this is a simulation done for the W1st AFTA report, showing simulated planets around stars up to 20 parsec, I believe. So 4 planets per star up to 20 parsec using distributions that are derived from Kepler. And you see that if you trace the capabilities, the expected capabilities of TMT, ELT, and space-based coronagraph, you see that the 2 domains are actually perfectly complementary. In space, we can go deeper because we are so much more stable, but telescopes are smaller, so the inner working angle is a bit larger, typically 0.1 arcsecond, while with the giant telescopes, with an aperture that's a factor of at least 10 or even 20 larger, you can push the inner working angle, but the contrast, of course, is much more challenging to obtain because of the atmosphere. But you see that we are going to probe 2 different spaces here in this parameter space, which is great. It means that we don't have to really argue anymore. We don't have to argue anymore about what to build. We need both, of course, and there's going to be a lot of work for everybody, for all of you. Of course, one does not simply build a coronagraph for a giant telescope, and we want you to help us solve these issues. Thank you. So if you want to image and characterize an Earth around a solar type star, I would say, yes, you need to go to space. Now, there might be Earth-like planets lying around M stars, and that can be done from the ground. But we want to go after all of them, so